World models sound abstract, but the practical problem is easy to describe. If a system is supposed to learn how the world evolves from observation, it needs a latent space that keeps meaningful differences alive. When that latent space collapses, different situations start to look dissimilar inside the model, and planning becomes fragile or unhelpful. That is why anti-collapse work matters so much. LeWorldModel is interesting because it claims stable end-to-end learning from raw pixels with a simpler recipe than many people expect. The public framing connects the work to JEPA predictive modeling and makes a strong pitch, no stop gradient trick, no exponential moving average teacher, and no frozen pre-trained encoder just to keep training from falling apart. If that kind of stability holds up, it matters beyond one paper. It would make pixel-based world modeling easier to train, easier to compare, and potentially cheaper to deploy in systems that need predictive representations instead of only next-dictone text behavior. The core claim is narrower and more useful than the hype version. This is not a declaration that world models are solved. It is a claim that a JEPA all setup can stay stable on raw pixel prediction without relying on several extra support mechanisms that often appear in these pipelines. The reported structure pairs an encoder with a predictor and optimizes next embedding prediction while adding SIGReg, a regularization term designed to keep the latent space diverse and well-shaped instead of drifting toward degenerate representations. That matters because once the training recipe gets too dependent on special moving parts, it becomes harder to know which ingredient is doing the real work. A cleaner recipe is easier to study and easier to reproduce. So the signal here is not only the headline performance numbers. It is the suggestion that anti-collapse behavior might be achievable with fewer crutches, which would make future world model experiments more interpretable as engineering systems instead of delicate lab setups. People care because the paper-level payoff sounds practical, not merely conceptual. The reporting around the world model highlights far fewer tokens than DINOWN and much faster planning in the tested setup. Those claims matter because world models are not useful only when they are clever. They need to be tractable. If a model can learn predictive structure from pixels with a lighter training recipe and then support planning more efficiently, that changes the cost story around experimentation. It could lower the barrier for research groups that want to test planning-oriented architectures without inheriting an excessively heavy pipeline. But this is exactly where careful reading matters. Efficiency numbers are only meaningful inside the benchmark and implementation context that produced them. They tell us the system was promising under the reported setup. They do not automatically tell us how performance transfers across tasks, scales, domains, or real-world deployment constraints. So the right takeaway is strong but conditional. The reported efficiency gains are the main reason to pay attention, not yet a reason to treat the problem as closed. The open question is generality. Results like this are exciting because they suggest a simpler path through a real bottleneck. But the public evidence still comes from reported benchmarks and one family of training decisions. That means the boundary is not whether LeWorldModel is clever. It clearly is. The boundary is whether the anti-collapse story remains reliable once you change domains, data regimes, task structure, or downstream planning demands. There is also a broader conceptual caution. A stable latent space is necessary for useful world modeling, but it is not sufficient for every kind of robust reasoning or control. The jump from a benchmarked world model results to broad system capability is where people often overread papers. So the disciplined position is this LeWorldModel looks like a meaningful engineering simplification with encouraging efficiency and stability claims. What it does not yet prove is that the hardest parts of predictive world modeling, transfer, and general deployment have become easy. The stable takeaway is not that one paper has rescued world models forever. It is that the anti-collapse problem is still central, and cleaner training recipes are often more important than louder model branding. If LeWorldModel does reduce dependence on training tricks while preserving useful predictive structure, it points toward a healthier engineering direction, fewer hidden stabilizers, more understandable objectives, and lower friction for future iteration. That is why this matters for people building AI systems, not only for those reading papers. Good infrastructure often arrives disguised as a smaller methodological simplification. In this case, the simplification is not trivial. It touches training stability, efficiency, and reproducibility at once. So the strongest interpretation is measured. LeWorldModel does not end the argument about world models. It sharpens the argument by showing one path where a simpler objective plus the right regularization may keep pixel-based predictive modeling from collapsing under its own training dynamics.